ninth lecture for the advanced electric drives. Okay, so we are discussing the design of controller now for the separately excited DC motor drive, and we have seen that how to use the tools such as Bode plot and no other things. So I hope there is no confusion in that section, right? I am not repeating that part now today, so that is fine for all of you, right?
Yes, sir.
Yes, sir.
Okay, okay, good. So first we tried to design the PI controller for the current control loop, and what we are finding that there is some non-linearity in the equation, in the electrical equation. So we tried to compensate that through a feed-forward term, and this is the common way of compensating anything which is any component which is non-linear. You feed forward it in the controller output so that controller doesn't need to worry about what is there on the other side. So this is what we do, and then the control loop looks like this. So
Sir,
because this is EB is already compensated, so we can remove these two disturbances together. Yes, any questions here?
sir, sir, we are designing PI such that sir, non-linearity will not be affected. Sir, hello.
Yeah, I didn't get your question. Ask again, Shambhunath. Shambhunath or Ashish? Ashish is
Sir,
asking.
Ashish. Yes, sir.
Yes,
Sir,
Ashish.
sir, this X is somewhat equal to EB.
Yeah, not EB exactly, but X into VG should compensate EB. So basically X is EB by VG. So we have the
Yes.
gain in between coming over here. Yes.
Yes, yes, sir. I was having doubt that if X is equal to EB, then sir, equation of IA will be a little bit.
Yeah. So basically this gain is there. So X should be this. So
Yes.
just take care whenever we are designing or doing the simulation, we need to keep this in mind. So this is always divided by this gain, whatever you are putting over here.
Yes.
So one way to identify is see the whatever is coming at this end, at the converter end, this is all basically a signal. When this signal is getting multiplied by this gain, then it is becoming voltage. You understand the point, right? Whatever is coming out of converter, that is voltage. And whatever is going inside the converter for control, that is only signal. So it may vary between 0 and 1. Okay, this is how you need to identify and understand what is flowing in the system.
Yes.
Correct? So many a times we can also put a limit over here that output should not be more than 1. So because our ramp is going between 0 and 1, so anything if it goes beyond 1, then it's of no use. So it should be between 0 and 1 for proper comparison. Correct? I'll discuss a little bit more about this today. So first let us complete the controller design. So now we have done this, and then we have the simplified control loop where we can find the open loop transfer function, something like this. So what we can do, we can rearrange this and make it in the form of some gain and then maybe a zero and then a pole. So like that we can arrange, and what we see that in this system we have a slow pole which is basically restricting the system to perform faster or to respond faster. So what we can do that we can compensate this slow pole with our controller 0. So this controller we have installed there. So we can maintain the value of Kp and Ki such that it is equal to La by Ra. So then there is no problem, right? Fine, right? Yeah, keep your mics on, no problem.
Yes, sir.
So two parameters we need to design whenever we are having the controller, PI controller, KPI and KII. So obviously we need two equations. One we have got over here. Now the other equation we can get from what our requirement is for the system. Let us say this is the open loop transfer function what we have got after the cancellation. Then we have the closed loop form over here. So if you see that here, when you draw the Bode plot at this corner frequency, which is coming something like, say, omega x is KII Vg by Ra. So at this, it will start going down with minus 20 dB per decade. The actual magnitude plot will be like 3 dB away from this point at the corner frequency. So then actually this is defining the bandwidth of the system, because at this frequency our gain is reduced by minus 3 dB. So which is the definition of bandwidth. So then we can say that yes, omega x is something which is our bandwidth. Now the question comes, if this is the bandwidth of our system, how much bandwidth we can have? So we have seen that faster or higher the bandwidth is, faster the response is. So if 3 bandwidth I have drawn over here and the step response corresponding to that. So this is the relationship, like if the bandwidth is higher, response is faster. By response I mean sooner it reaches its value, the whatever input value we have given. So actually the bandwidth and time constant of any system are basically inverse of each other. So tau is nothing but 1 by b omega or bandwidth. So then we need to understand that how much bandwidth is actually good for us. We cannot have any value of bandwidth. Let us say if you keep very small, this b omega value very small. So what will happen? The system response will become very sluggish. So no point in having such system, right, which is very sluggish. So what we can do, we can increase the bandwidth. But where is the upper limit? The upper limit lies in the practical limitation of the system. So what we are basically doing, that we are generating this output from the converter through this PWM operation. So because this is associated with this kind of comparison and then the output, so this must be constrained by what is the frequency for the carrier. That can also be called as switching frequency. Correct. So general thumb rule I have told that you can consider the bandwidth to be equal to 1/10 of the switching frequency. So during the course we will have more discussion about why 1/10, why not something else, or if can we reduce this 10 to some other value, can we increase this to some other value. These are discussions we will have. But as of now, take it like a thumb rule. So then once we have said that, then our second equation is also ready. So KII Vg by Ra is nothing but our bandwidth, omega b omega, which is nothing but 2 pi fsw by 10. So we have got our KII and then we can get our KPI. So we have designed both the parameters of our control system. As a result, what we have now, the control loop now is defined something like this. It has reduced to this form where tau I is nothing but whatever we have seen earlier, this expression Ra by KII Vg, 1 by b omega. Correct. So now this is like a first order response. So if you give any step response or step input to your current, the armature current, corresponding to this control loop, it will respond something like this, where this settling time will be defined by what value of bandwidth you have chosen. So generally 5 times of time constant is enough to settle it within 98% or more of the actual value. Correct? And this is first order response, so it must not overshoot. Do not draw it like it is overshooting then coming down. That's not the response for first order. Okay? So these things you keep in mind when you are drawing it yourself. So that is how this is. Now we have designed the current controller. So any doubts up to this? Any of you are having any doubts, any questions? Then I will move to this speed control part.
Sir, one doubt, sir.
Yes.
So, like, what is the mathematical relationship between the bandwidth and the time response? See, like now you have simply told that as your our bandwidth is increasing, our time response is increasing, like time response is reducing. But how they are mathematically related? So that part is not clear.
This is what I am telling, right, Deepak?
Yes, sir, but like you have directly given in terms of this thing. But if I see with respect to time response and with respect to frequency response, how we can correlate both of them?
That
If
is what I am correlating here. See, S by omega is what is your corner frequency, and 1 by omega is written as tau I.
that part is clear, but uh, like frequency domain and time domain, how to compare? That is where like
So
I get
what is
doubts, sir.
what is frequency and time relationship?
Yes,
Are
sir.
they not inversely equal? Like, are they not inverse of each other?
They are inverse of each other, sir. That is true.
Hmm.
But in like with respect to settling time and those things, because
Yeah, so just multiply by 5 times.
that
Your
is
T settling is equal to 5 times of tau. That's what I am saying. 5 time constants it will take. That's the general view about this. So basically, in one time constant, it will reach up to the 1 by e value, something like that. It will keep
60% that will be
progressing.
there. Yes, sir.
Yeah, 1 by e times of the actual value. So what we say that within five time constants, practically it will reach to that. Theoretically, it will take infinite time to reach actual value because it will keep progressing towards the final value. Still, there will be some delta error. Very, very small, minute error will be there. But that is insignificant for us, right?
Yes, sir. That
Correct.
error we can ignore.
Yeah, so we say that yes, in 5 time constants, it has reached the practical values of whatever we want. Fine.
Yes, sir.
Okay. Anyone else having any other doubt? Fine. So now let us come to the speed control design. Again, we are putting the PI controller. So this is okay. We can have the, okay, let me draw it little bit more clearly here. So did anyone of you try uh, deriving what are the components Kp omega, Ki omega? Did you try on your own?
Yes, sir.
Okay, so are you able to get the expressions, Ashish?
Yes, sir. By
Good.
magnitude and phase angle.
Good, good, good. Okay, so then we, after the current control loop, we have the torque generation, load torque, and then the first order response. So what we have said that because this speed measurement is little bit noisy, even if we are estimating or if we are measuring it directly, so that's why we need some filter over here. So which I have said that is having something like this, where tau f corresponds to 2 pi. Say 10 hertz is the frequency, cutoff frequency for the filter. That is usually a good design because speed is more or less a DC quantity. So 10 hertz looks like a good number for this. Correct? Now, this is what we have. So here clearly the tau L is something coming externally. No, it's not within the system. It is externally applied. So it may be there, may not be there. So for control design, we simply ignore this part. And whatever, whenever this is applied, the compensation has to come from the controller. So that controller has to work like that. We cannot help. So another thing what I have told regarding this first order speed subsystem is that the time constant j by b is something very, very large. Let us say some tenths of second or let's say 1 minute, something like that, based on how big the system is. Now, the value of B could be very, very small. So what we generally say that in the worst case scenario, B could be equal to 0. This is our worst case scenario. So we consider this for our design. If it is able to work for this condition, then it will be able to work for any better scenario. Correct? So now, after having these two things here, the open loop transfer function we have written. And I can combine these two terms and then the filter part. Correct? Then I suggested that because we are dealing with poles which are sitting at origin, so here also it is at origin, here also one pole will come out at origin, and these two poles are little bit far. So tau I said no, may have some value corresponding to say 0.01, and tau f may have value corresponding to say 0.1 second. So then what we can do basically, we can combine these two poles which are little far and we can make one common term out of it. So when we combine these two terms, this is what we are getting actually. But because this term is very, very small, say tau I into tau f will be something of the order of 1 millisecond. So what happens compared to this term, what is coming over here and 1, this is very small number. So we can kind of ignore, and then the approximate term for this combined whole could be this tau 1, tau f plus tau y, which maybe I can write as another term tau 1. Okay, so then the open loop transfer function gets simplified a little bit.
So,
Yes, Ashish?
so this filter is working as a feedback or it is in the same path?
It is in the feedback path.
Sir, when we are writing the open loop transfer function, sir, it is. So when we are writing the open loop transfer function, then 1 plus 1 by 1 plus s tau f is so multiplying on the same path.
Yeah, that is how we write the open loop for this kind of system. Okay, that is how any control loop when we are having the open loop transfer function is written like this only. All the terms are simply coming over here. That is the way.
And also, sir, we can make this transfer function as unity feedback. If we make this unity
We
feedback,
can
then
make, but then see what I told, no, there are practically some constraints which we cannot avoid. Say for current measurement, we can be very accurate. Current sensors are good. But problem with the speed sensor or speed estimation is that it could be noisy sometimes. Okay, you will see during the later portions of the class that why this filter is necessary. So then we need to put something to remove all those noises which are coming on the system. So something like a 10 hertz, because our speed, this quantity is DC. So 10 hertz looks okay, there is no problem. Correct?
Yes, sir.
yes,
So then if we simplify the expression, and let me also write it in the proper form. So this is fine, right? Any confusion up to this point? Okay, we have simplified a little bit. Now what we have basically, what I told yesterday as well, that we have two poles coming at the origin. So I can basically combine these two terms and then we have this double pole at the origin. So what it will do basically, that the gain and phase plots, if you draw here, this will start with minus 40 dB per decade and phase will already be at minus 180 dB. So which means our system, whatever we are getting over here, is unstable. The phase margin is basically zero. Correct? Phase margin, you understand, right? This is nothing but whatever phase you have plus 180 degree. So how much gap you have from this minus 180 degree line, that is basically the phase margin. Correct. So this is basically zero. Then the system is inherently unstable. Now, even if we try to cancel this pole zero, whatever are coming over here through our controller, this is not going to help because the poles which are actually defining the dynamics are sitting at origin. So what we need to do, what I told yesterday also, that we need to position this zero and pole such that at the gain crossover frequency, our phase margin improves to some non-zero value, some positive value. Correct. And that method, what I was suggesting yesterday also, is called symmetric optimum method. To make it more accurate, this term, you can say symmetric optimum phase method. So phase we are optimizing. And
Sir,
what
why don't we place zeros as well as at origin?
how will you place someone?
Sir, by uh, by manipulating Kp omega and Ki omega in such a manner.
You tell me there is 1 plus this term. What can you manipulate here?
Sir, using a KDS differentiator controller.
That also we will do. But still it will not create a zero at the origin, right?
Yes, sir.
Will it create? Do you want to simply put a differentiator? That's a different issue. That is another big problem. What you will create? What is differentiator basically? This is something like dx by dt. So if x is something like sine n omega t, let us say, what will be dx by dt? N times of cos n omega t. Your each and everything is magnified by this order of the frequency. The differentiator alone is a big problem.
Okay,
Okay,
sir.
never ever use. And there is purpose for different things when we try to have differentiator in the system, that means the KD part. There are different ways how to use it and where to use it. There is different reason. But with PI also we can work, there is no problem. Understand my point?
Yes, sir. Yes, sir.
Good. Now, this is what I have been saying, that we use the symmetric optimum method, and what we try to do, that that we improve the phase margin at the gain crossover frequency such that it is some positive value. So phase margin greater than 0. So let us see what happens. Let's say this transfer function, if I write again little bit better manner so that it is easy to recognize, we have ki omega by j, think that's the term, and then 1 by s square. Okay, so I am writing this as s by omega z, and I am writing this as s by omega p. So we are going to position, so obviously omega z omega p mean whatever is written in these two terms, right? So we are going to place our 0 and pole such that this phase improves. So obviously we need to position the 0 first, right? Say we are putting our omega 0 over here and omega pole somewhere here. So what will happen? Characteristic which the gain characteristic which was going as minus 40 dB per decade, maybe it might have touched 0 somewhere here. It will become minus 20 dB per decade, and it will continue up to the omega p, and then again it will become minus 40 dB per decade. Correct? There is no problem in this. So now our gain plot is crossing the 0 dB line with a slope of minus 20 dB per decade, which is okay. So which means the phase will not be 180 degree, it will be better. So what will happen to the phase? Before this omega z frequency, it will start improving. And it will reach to some value and then it will fall again, and after omega p, so like 10 times of omega p, it will again go and merge with minus 180 degree. Now here what we see, we will have some positive phase margin. This is what I am saying as the symmetric optimum method to stabilize the system. Understand the point? So if you plot this asymptotic, it will look like that. If you want to plot more actual, so it will be little bit smooth curve. Nothing much difference will be there. Fine. So by using this positioning, what we have done, we have made our phase margin positive. But how much phase margin is good? This is the question. So we say that, okay, if we have at least something like 45 degree phase margin, this is good for the system. Correct. Now we need to have the values of this gain crossover frequency. So this is basically, we have seen that this is actually our bandwidth. So bandwidth or this thing, the gain crossover frequency and the phase margin, these two things we have to decide along with the Kp omega and Ki omega. So these unknowns we have. Now what this method suggests, that the gap, whatever we are having between these two corner frequencies, this should be equal, say A. That is the meaning of symmetric. We are symmetrically placing the 0 and pole around the crossover frequency. So in effect, what will happen, that our omega b omega is basically A times of omega z, and omega p is A times of omega b omega. So this one relationship we have got, right? Now what other relationship we have is that the gain of the system at omega equal to omega b omega is how much? What is the gain value?
1.
Yes. This is 0 dB line. 0 dB means the log, this is 0. So then this is 1 basically. So the gain is unity at this point. Correct? And the third relationship what we have is that the phase margin should be 45 degree, which means the phase what we are saying should be something like minus 135 degree. Phase of the at omega b omega. These four equations what we are having will help us in design the parameters of this speed controller. Correct? We have got all four. So now let us go one by one. Let us first see this phase. So what we have basically, if we have to take the phase of this open loop transfer function, then we are basically taking phase of kii by times c by j plus, or rather it should be minus the phase of s square. Then we have the phase of, let us say, the pole what is coming s by omega, sorry, 0, and then we have the pole 1 by, or it becomes this thing when we are writing minus, so already this is taken care. So phase of s square, and then here 1 plus s by omega p. Correct? So this is 0, there is no problem. This is 180 degree. There is no problem. This and this we can write. So what basically we want? We want something like 135 degree phase. And we have minus 180 degree already due to this double pole. Plus this here can be written as tan inverse of omega by omega z. And minus tan inverse of omega by omega p. Any problem in that? No, right? We are simply using whatever we have done earlier. Now, what this becomes in effect, that tan inverse of omega by omega z minus tan inverse of omega by omega p is basically equal to 45 degree. Now, if you recall, we are doing this at frequency omega b omega. At this point, we want this phase, right? So at this point, we have a relation between omega b omega and omega z. What is that? Omega b omega is basically a times of omega z, and omega p is a times of omega b omega. This we have already. A is also unknown. We have not defined what is A. We only want this much of phase margin that we have said. So now this can be simplified again. So this becomes tan inverse of A minus tan inverse of 1 by A is equal to 45 degree. Okay, so can you suggest what to be done next? How to solve this?
Tan inverse of a minus 1 by a divided by 1 plus a into.
So simple, tan inverse A minus tan inverse B, and this way we can combine this, and which is equal to this. So basically, in effect, what it means that A minus 1 by A is equal to 2. Isn't it? So what we will have is that A square minus 2A minus 1 is equal to 0. Any problem in that? Simple quadratic equation. What are the solutions of this?
Sir, that is root 2, sir. Tan
Which
of
one?
45, tan of 45, 1 by root 2. Means
Tan of
a square.
45 is 1.
No, one sir.
Sine of 45 is 1 by root 2. Cos of 45 is 1 by root 2.
Yes, sir. Yes. That equation.
Sir, 1 plus or minus root 2.
1 plus minus root 2. This is what we are getting as solution, right?
Yes, sir.
Now A is basically a ratio. So ratio cannot be negative. A must be greater than 0. So basically we have only one solution which is coming over here as this. Correct? So one relationship we have got for our A. So we know that our pole is basically 1 by tau I. This is known already. So if A is known, then we can say what is omega B omega is basically omega P by A. So this is also known. Correct? What is omega Z? Basically Kp omega by Ki omega. This is the thing, right? Or it is inverse of this. Let me just check.
Ki by Kp, sir.
Inverse, sir.
Yes. It should be inverse. Correct. So this is basically I can write as 1 by omega Z. So which is coming equal to A by B omega. Or in effect we can say that Ki omega by Kp omega is basically omega B omega by A. So one more thing is known, right? Now still we need one more equation to solve this one of the parameter. And this information will come from our last equation. What we have said that the gain at omega B omega is equal to 1. Correct? No problem in this so far? Fine, right? Everything is well defined. There is no issue. So now this we have to do. So obviously now if we
Sir.
take gain of the transfer function, yes, Shambhunath?
Sir, that is omega p equals to 1 by t1, sir. That is ti plus tf, isn't it?
Say again.
Sir, in the upper slide, sir, omega p equals to 1 by t1, sir.
Omega B equal to?
Omega p equals to 1 by, sir, t1 means ti plus tf, sir.
No, the pole is here, right?
The same only, sir. What he's telling is right. T1.
Yeah, tau 1.
Yes, sir. Yes, tau 1.
This
Yes,
is
sir.
this not correct?
Yes, sir. It's okay.
So now quickly let us write the gain for the system. So this is just magnitude, there is no problem. Then we have omega square, and then we have root of 1 plus omega square by omega z square, and then we have the root of 1 plus omega square by omega p square. Basically this is inverse. Okay, and this going equal to 1 at omega equal to b omega. Fine. Again we know the relationship between all these things. So what we have, ki omega c by j times of 1 by omega b omega square. This is defined. What we have here, what is the ratio here? It is a square simply, right? Omega b omega z is a. Omega b omega basically. And here what we have? 1 plus 1 by a square equal to 1. There is no problem in that, right? So then you can simplify this thing very easily. Now only one unknown is here, which is ki omega, and rest all things are very well defined. Square, then if you simplify, this will come out to be a, isn't it? So a square plus 1, this will cancel, a will come over here, and then this is what is the kind of we have solved this ki omega. So now can you get the exact expression for ki omega? So all the unknowns we have solved in our controller design, right?
Yes, sir.
So now we can say that with these design parameters, we will have some phase margin of say 45 degree. You can keep anything else also, and then you can solve it again, and the values will change. So whatever
Sir,
phase
can
margin,
I?
yes,
Sir, can I
Shambhunath.
take phase margin? Can I take phase margin as 60 degree?
Yes, you can take.
Yes.
Okay. So whatever value we take over here, that will basically define how your step response is going to behave. So for example, for this kind of phase margin, the typical step response is going to look like, say this is your reference speed given. So what will happen? This will have some overshoot and then this will settle. Something like this. So this overshoot, how much you want to have, is basically dependent partially on the phase margin and somewhat on the bandwidth. So again, bandwidth will define that how fast it is reaching over here, and the phase margin will tell like how well it is settling. That means how much overshoot you are having over here. So the response will be a typical second order response because our system is more or less like that, and this kind of speed response you will see for a given step input. Fine? This is fine, right?
Yes.
Any
sir.
confusion, any question? So we are completing the DC-DC, or you can say the DC motor controller part over here. That means we will move to our next section, which is basically induction motor in the next class. So any doubts, any questions you have, you can ask now. Fine? Okay, we will have one more chance on next lab class. So there also you can discuss. Just think about all these things, whatever you have learned, and yes.
So actually, like now you are telling that we are placing this omega bandwidth symmetrically. But if we place omega bandwidth 2 decades away from your omega z, then we will have the maximum phase margin of 90 degree. So will that
omega
not be?
bandwidth you can do,
But
but
that only
again,
thing what I understood is there my response will be very slow because my omega bandwidth, like what Sampan has asked, if we shift the pole towards zero or zero towards uh, zero, then only thing is my omega z is becoming very slow. Response overall. So is that the only reason, or is there any other reason?
One more point what I have missed to tell over here is that, see, we are having some omega b omega based on some phase margin and based on what we want. So where is the limit on all this? Can we have like 70 degree, 80 degree, 90 degree, whatever we want? You understand my question? Okay. See,
Yes.
the point is that we are having this cascaded control. So we have a speed controller, which is basically containing the current controller. And then we have the system, which is giving omega, and this is coming over here with the filter. Now, obviously, when we are having this current control loop inside here, the outer loop cannot be faster than that. That is one constraint. When you say we can be very slow, let's say we don't mind going like response time of 1 minute, fine. But the upper limit is that this system, the bandwidth of this system, the outer loop cannot be close to or more than this current control. So this is the upper limit. Omega bandwidth, or if I write the frequency, again a thumb rule, try to keep it something like f bandwidth I, if I say, and this is omega, 1/10 of the inner current control loop. So that way what will happen? This inner current control loop will not interfere with the outer speed control loop. So this is something like max, you can say. Sometimes we violate this limit also, that is okay, but under given conditions. So in general, as of now, you take this also as thumb rule that whenever you are designing this, how much phase margin, how much all these things, you definitely see that what bandwidth you are achieving for the speed control. If it is going close to the limits, then the system may not behave very well. Although you have designed and done everything, But you cannot say that my current controller is having bandwidth of 100 hertz and my speed is having something like say 50 hertz or no, 80 hertz. This kind of bandwidth is not allowed. Fine. Fine. Clearly understood the limits over here.
Yes, sir.
Yes, sir.
Clear? So this one thing I missed out. So yes, the questions what you were asking, this is the relevant answer for that. So again, we have relationship over here, no, FSW by 100. So these are all related. Nothing is coming randomly.
But sir, in between you told what is the maximum phase margin we have. So what is that limit?
See, that's what I'm saying. This what is maximum phase margin is dependent on how much bandwidth you are
Okay.
trying to achieve.
Okay, okay. Okay, sir,
Correct?
understood.
That is what we should keep in mind while designing.
But like as you already said, we can go with as low as possible. And
Yes.
normally we are assuming, like let us, if we assume that the filter is a unity feedback system, in that case, like we can go phase margin up to as high as 90 degrees. So whether that will be a better scenario, like where is the optimum level for this phase
Good.
margin?
So the simulation work given to you, try doing it without filter, with phase margin 90 degree and all that. So you will see how it is coming, right? So some things are better told through what you do. So do it practically. Do it yourself and see how it is coming, how the response is. What do you call a good response? Fine? Is that fine, Deepak?
Yes, sir. Thank you. That is clear.
So this, I'm telling one way to design, no, some example I'm giving. You can take another way of doing it, designing it, and see what benefit you are getting. Correct? These things are not, I'm not saying this is the only way to design. This is one way, which is little bit more systematic than randomly putting your KPKI values, which generally you do. So which is not a good thing actually.
Normally,
Okay, just
okay, sir.
okay. So just one more minute I will take now to summarize whatever we have seen so far. So something like controller we have designed. Now, when we are implementing in the control system, let's say in the simulation, what we basically have is, let's say here is our controller, which is generating the reference for the current controller. So, okay, the comparison will come. Let me draw that also. Then we have the controller for current. Here it is omega controller. So this is what is basically our control structure what we will have in this simulation. After this, it interfaces with our physical system. What physical system we have? We have the power converter. We have the motor which is getting fed from this power converter, and then whatever load you attach. So feedback is coming from this motor and the filter is, let's say, placed over here. Whatever VREF you have generated, and of course after the compensation, this X, this is basically a signal V star. This will be fed to the converter in form of the PWM signal. That means this will be compared with this type of ramp, and the output will basically be a gating signal for the converter. You understand the structure? This is where our controller is interfacing with the practical system, the simulation model you can say, or hardware or anything. So this all we have defined, let's say designed mathematically, but when you are implementing, it's not just gain over here. Whatever output you are getting, you need to compare with the ramp, and that will generate the gating signal which is to be given to the converter. And of course, this converter has some DC input that is already connected over here. The output will be fed to the motor, and then whatever load you want to interface. This is how typically your control actual simulation would look like. Fine. These are actual motor models, actual converter, which means IGBT or MOSFET or whatever you want to have, all these things over here. Fine. So
Yes, sir.
let me stop over here, and this is all about whatever DC motor control we will have in the class. So go through it once again, try to design the simulation exercise what I have given, try to do the assignment. One more will be given on basis of this control and other these part. So you can try